application and negative feedback. So let's start the session. Friends, if you have the system like this is the feedback element, this is the gain element, and they are connected. Let's take in this way. Here I'm taking output from the feedback element. I'm taking output plus V0 over here in this way. At the input stage, they are connected in shunt like this. So here it's clearly you can see over here that at input stage this is shunt, at output stage this is series. Okay. This is series and this is shunt. So this is topology. Okay, configuration of your amplifier, that your amplifier is shunt series amplifier. So which topology they are connected in? The topology is shunt series, or the other name of this is, for the series it refers current and shunt. Can I write it over here? If I'll write name, so this represents output and this represents input. Okay friends, but in the examination sometimes they will give some circuit and they'll ask which type of topology they are using in. So you have to identify there. So they will not give circuit like this in which you can easily see and can reply. No, they will give the circuit little bit different. So let me tell you some parameters related to the how to identify the topology. Then I'll give you the problems. Okay. Wait a minute. First point to identify the topology is, suppose you have OPAMP circuit. If this OPAMP, this is load resistance, suppose like this. If your feedback is going before load resistance, if your feedback is going inside, so this will be definitely voltage source. Though this is related to output, so I'm using voltage source. If the terms related with input, I'll call the control. It's voltage control or current control. Here I can use voltage source. And if your feedback will go after the load, so definitely it will be current source. Is it okay friends? And inside over here at the input stage, suppose you have two terminals, right? Positive terminal and negative terminal. So if anything will be connected with this non-inverting terminal, so it will be definitely voltage control. And something is connected to negative terminal, it will be always current control. Okay, and apart from this, if at the input you applied some voltage, so it will be voltage control. You applied current, so it will be current control. We'll see in the problems. Okay friends, now this is how information I gave you, but this is for OPAMP. Now I'll give you for transistor also. Suppose this is the transistor circuit. Let's take like this. This is base, collector and emitter. So if I'll use feedback from emitter terminal, I'll call it series. If I'll take from collector terminal, I'll use shunt. And for base also it will be shunt. Okay, just remember like this. Now I'll show you the application of these two concepts. Okay, let's take a circuit now. The circuit given is, let me take the circuit over here. RC, VCC, over here transistor is connected. This is BJT actually. This is the input stage. Input stage I applied current and it's grounded. This is the feedback over here, feedback resistor. Feedback resistor is RF. Now they are asking, here they are taking V0. The question is, which type of topology it is? Find out the topology. And the options are voltage control voltage source, option B, current control current source, option C, voltage control current source, and option D, current control voltage source. So earlier we have seen in the BJT, if you are taking something from collector terminal, so definitely it will be shunt. It will be shunt and it's going to base terminal itself. So this one is again shunt. And at the base terminal we are using current. So definitely it will be shunted. So your topology is shunt topology. Shunt topology. This is input, this is output. Who is shunt at input? Definitely current. So this is current control. Who is shunt at output? Voltage. So this is voltage source. So the topology is current control voltage source. Current control voltage source. So this is trans resistance amplifier. Am I right? This is trans resistance amplifier. Okay, friends. And the other name of shunt is shunt other name. First, I'll consider the output. What is the output? Shunt. Who is the shunt at output stage? Voltage. So I'll call it voltage. Now input. Input is shunt. So this is voltage shunt. Okay, friends. Now let's check another one. The circuit is given RC. This is two-stage BJT. V0. Over here, it's grounded. This is connected over here. Another, this is Q1, Q2, R1. This is grounded. And this is, we applied some source over here, like this. And you are taking feedback from this side, and feedback is RF. Feedback is RF. Okay, friends. So now they are asking, the question is same, which type of topology it is. Find out the topology. Again, the options are same for you. Now, if you remember, I told you earlier how to identify topologies in terms of BJT is given. So the feedback is taken from output. So it will be definitely shunt over here. And it's going to the emitter. Emitter means I told you will use series. So this is series shunt. Series shunt. Series shunt, the other name is, who is shunt at output? Voltage is shunted at output. And input is series. Okay, friends. So this is another name. And in terms of, see, series, who is voltage control? Shunt, voltage source. So this is voltage control, voltage source. This is the voltage amplifier. Okay, friends, let me take another one. So circuit is given. The OPAMP circuit, this is RL, load resistance. And after load resistance, the feedback is going in. So you can easily understand after load means current source will be here. Okay. This is the feedback element. So total elements are 3. This is feedback box. Okay. Over here, it's going to minus. And at the positive terminal, we applied voltage source. So which type of topology it is? So at the input stage, it's a voltage control. At the output stage, it's the current source. Why source? Because after load, you are taking it. Okay, so I can say it voltage control current source. Okay. Let's come to the next part. And the next part is given here. The OPAMP circuit, minus plus, this one is grounded, over here load resistor RL, and this is R1 grounded, and at this point they have taken the feedback. This is feedback resistor RF, perfectly fine. This is IS plus minus. It's like this. Now we have to identify which type of topology it is. Okay. So see, if this is the current, if this is the current, feedback current. Now after load we are taking it. Is it okay? After load you are taking means this is current source. Current source at the output stage is series. So at the output stage it's a series combination. And at the input stage, see at the input stage if you will see it, the current source is applied to the negative terminal. So negative terminal, I told you earlier, it will be shunt or it will be current control. Is it okay? So this topology is shunt series. This is shunt series. Okay friends. So I hope now it's easy to you to identify which type of topology is there in the system. Now in the next we'll see the effect of feedback over the gain. Okay. So this is the, I can say we'll see R in and R out of feedback amplifier. Feedback amplifier. Okay friends. So we have 4 type of feedback amplifiers. So number 1 is, let's take it in this form. Voltage control voltage source. The other name of this is series shunt. Series shunt we have series, we have shunt, and we have shunt. Let me take over here, shunt and series. Okay friends, shunt and series. So this is related to input and this is related to output. This is related to input, this is related to output. Suppose we are having parameters. The input resistance is Rin in the original circuit. The output resistance of the original circuit is R0. Now you use this type of topology. VC-Vs you used. So in the VC-Vs, there will be changes in Rin and Rout because of this feedback circuitry. So series, if the input connection is series connection, definitely your Rin going to increase. Okay. And your Rin will always increase by 1 plus A beta times. 1 plus A beta times your Rin will increase in this case. If the output is shunt, so your R out will definitely decrease by the factor 1 plus A beta. Is it okay? So R0 will be multiplied with 1 by 1 plus A beta. Similarly over here also in the series, the same thing is going to happen. A beta. In the both cases, the resistance will increase. If they are shunt, so going to decrease here. A plus A beta. This is the factor by which you have to multiply or divide. R0 1 plus A beta. Here R in 1 plus A beta and here R out 1 plus A beta. Is it okay to you? This is input and output resistance, or I can say the effect of feedback over the input and output resistance. Okay. So this is series shunt. This is voltage control voltage source. What about series? This is voltage control current source. What about shunt? This is current control voltage source. And what about shunt series? This is current control current source. Okay friends. And the other names of these topologies we discussed earlier. The VC, suppose you have VC CS. So you can write for this is series and series. Either series, because voltage at the input is series, current at the output is series, or you can say in the output input form, output is given series. So take the name of series, name is current, input as it is. So you can say it, this is current series also. The voltage control voltage source, you can call it current series. This current belongs to the output and this series belongs to the input. Is it okay? I hope it's clear to you, friends. Now we'll take problems and we'll finish this chapter today only. Okay. So this is the gate problem and the circuit is given. Let me draw over here. Grounded, RC, connected with VCC, again dual stage amplifier. Over here, this is load and the feedback is going to this circuit like this by R. V in over here and V out over here. This is load given. Friends, now the question is, the feedback amplifier shown in the figure has current series feedback, voltage series feedback, voltage shunt. You have options. Current series, voltage series. Next is voltage shunt. And the last one is current shunt. Okay, friends. So, see, this is the input stage and this is the base stage. And we have seen earlier the base is shunt. So, input stage is clear, it's a shunt. So, you are having only two options remain with you. Okay. Shunt means its two branches are connected parallel. Going to divide, resistance is going to divide. But though this is the emitter side, and earlier I told you, if anything goes from emitter, you have to take it series. Okay, friends. But see, at the same time I told you, if anything is going before load, means it's voltage source. If something is going after load, like this, it will be current source. This is very important formula. If these two things occur simultaneously, that from emitter you are getting, you are taking something after load, before load. So you have to take care of it. In other words, I can say, see, if you will observe this, what you will find is, if the current is coming over here, this is the sampling point. Over here, two currents we have. One is feedback current, one is load current. So current is going to divide. Current is going to divide means there are two circuits like this, two resistors are connected in parallel. Is it okay? Then only current is going to divide. Okay, friends. So this is shunt at output also. So output is shunted. Okay. Output is shunted. Input is shunted. So your topology is shunt. But in these terms, the options are not given. So let's take it. This is the output. Output we call the voltage and the input is shunt. So this is option C is correct. I hope it's clear to you. Okay. Let me take another one. So in this question they have given to obtain very high input and output impedances, you need very high input, means input R in and R out. You need high. High means series you need. If you want to do input high, you will take series. If you want to take output high, you will take it series. In the series both will be high, we have seen. But the options are given voltage series, voltage series, option A. Option B is given current series. Option C is given voltage shunt. And the last option is current shunt. So friends, you identify that this is series. Now in terms of output input parameter, how you will write it? Output. Who is at the output? Series. Series at output stage means this is current. Okay. Input stage as it is. So this is current series. Okay friends. Now the another problem is given. This is the FAT problem in which you have RD like this, RD over here, this is grounded, M1, M2, like this, it's grounded. Here I am applying current source I in. Okay. This is the feedback RF. Directly we are taking feedback from this point. Okay. Now the question is, in the AC equivalent circuit shown in the figure, if the I in is the input current and RF is very large, this RF is very large, the type of feedback, and your options are given voltage feedback. In this we have both voltage, only name. So this belongs to input, this belongs to output. Okay. And the B is volt current. The C is current volt. And D is current. So friends, earlier I told you, see, over here, what you are going to do is, you are taking this like this directly. Is there any division of resistance over here? Directly whatever current is coming into this is not going to divide in two parts. Okay. Before feeding inside, it's not going to divide. So at the output stage you have series. Is it okay? You can check in this way only. What is at sampling stage, what is at input stage. And here at the input stage, what is going to mix over here? This is mixing, right? And this is sampling. Okay. So sampling is series. Why series? The current is not going to divide. Okay. If we'll consider this at the output, the RF is given is very high. There will be no current over here. Okay. So directly what you are feeding over here? The series current you are feeding. So at the output stage, wait. So you are feeding current. Is it okay? What about the input stage? At the mixing level. Again the RF is very high. The current is not going to divide over here. This is also series. This is also series, right? So this is the series connection. Series is voltage and series is current. So this is voltage current. Okay, I hope it's clear to you. The question is the input impedance Zi and the output impedance Z0 for ideal transconductance. For ideal transconductance are, your options are given Zi0 and Z0 0. Option B is given 0 and infinity. Option C is given infinity and 0. Option D is given infinity. Transconductance. You need conductance. So at the output stage you need current source. At the input you need voltage control. So this is current divided by voltage is nothing but transconductance. Is it okay, friends? So transconductance, output divided by input is coming conductance. So this is transconductance. So voltage control means series. Series means infinity. Current source means infinity. Infinity, infinity. Option D is correct for this. Is it okay? This is 2014, 2 marks. And the circuit is VCC. This is RC. Okay. V0. RE. Grounded. Over here RS. VS. It's like this. But in question they have given in this only. Like this. The question reads is, the feedback topology in the amplifier circuit, the base bias circuit, is not shown for simplicity in the figure is. They are not showing the topology, but we have to identify which topology is given over here. Again, the options are voltage shunt, option B is given, current series, C is given current shunt, and D is given voltage series. So friends, nothing is given over here. So how you will solve it, or how you will get which type of topology is given over here? So at the input stage you applied voltage, right? So definitely it's a voltage over here. The controlling parameter is voltage. No problem at all. And what you are feeding? This is the mixing level. What you are mixing? You are mixing voltage. So voltage is okay. Voltage means the series. So your option will be B or D. Now let's check the output. At the output, how I'll get the feedback? Can I connect this like this? Is it okay? Or in other words, these are the same, grounded. At the output, what is given? I node. Means you are controlling your I node with the help of your voltage. It's kind of I node at the output stage, and at the input stage your voltage. So at the output stage I node is current and the input is series. So this is current series given over here. Okay. In 2017 they asked one question. A good transconductance amplifier should have. Again there asked transconductance. Transconductance means current source and voltage control. So voltage control means series. Current source means series. In terms of resistance, infinity. Over here, infinity. And options are given. High input resistance and low output resistance. Low input resistance, high output. High input, high output. So here, this is the case of high input and high output. Okay, friends. Now we'll see problems in which OPAMP and our diode is given. Okay, so diode concepts will also be cleared if you have any doubts. OPAMP circuit is given, minus, plus, grounded. Here it's given R1. Okay. You applied input over here, V in. No problem. Over here, you have diode circuit like this way, R2, and here it's like this, and here is your output V0. Okay friends, everything is fine. This is the circuit given. Now refer to figure shown below. You have four options. Option A, when Vi greater than 0, the output will be minus R2 by R1 of V in. The first option. The second option is given. When Vi greater than 0, your V0 is also 0. V in greater than 0, V0 0. Option C is Vi less than 0 and V0 minus R2 by R1 of Vi. Option D, Vi is less than 0 and V0 is 0. This is option D. Now let's check one by one. This is 2 marks question gate. So friends, if Vi, see this is the Vi given AC signal given, it means positive half and negative half, positive half, negative half. Let's take the condition Vi greater than 0. Vi greater than 0 if the circuit is inverting amplifier. At the output stage over here, the output of OPAMP I'm talking about, not about this point. At this stage you will get negative. Why negative? Because this will invert the input whatever you applied. And I'm talking about the positive half first. This is the positive half I'm talking about. Because in the positive half, its Vi is greater than 0. In this case, you will get over here negative. What this negative will do? Because of this negative, this will turn off. This circuit will turn off. This diode will go out. Because this will become in reverse bias. Let me remove it. It will be in reverse bias. The circuit will be like this. This one will conduct. So this, let me write over here. This one is going to conduct. Okay. So this is the circuit. Now our task is, what is V0? See, there is no current in this circuit. So there will be no drop over here. It means whatever in this entire branch, the voltage at this point is V0. This is the negative feedback device. Means the ground, virtual ground concept. Here 0, here 0. V0 is definitely 0. V0 is definitely 0. So for this question we have option. Option B is correct. Let's check a negative cycle also. In the negative cycle, this will be positive. When this will be positive, there will be, let me draw circuit again. Now I'm going to apply negative cycle to the system. Means the Vi less than 0. Okay. So the circuit was here R2 and here I'm taking V0. Over here diode in this direction given like this, and here the diode is given in this direction. Okay, and the negative half cycle, it will invert the input. Negative will become plus. So this is positive. Because of this positive, this diode will turn off now in this case. So let me remove this diode. This diode is no more in the circuit. Now your circuit is this. And this diode will become short circuit. This diode will become short circuited. So let me replace it. So this is your new circuit. In this case also you are getting V0 definitely. So can you get the V0? Yes, I can get. I can apply 0 over here. So 0 minus, the input is minus. Is it okay? Minus V in by R1 plus 0 minus V0 divided by R2 equal to 0. Okay friends. So this minus become plus and your V0 equal to R2 by R1 of V in. Do we have this option? No, we don't have this option anywhere. So in this case, option B is correct. Okay friends. Come to the next question. And next question is given very simple circuit. the circuit is given like the circuit resistance R given with V in connected with diode in this way, like this. Obviously this is inverting and this is non-inverting terminal. Non-inverting terminal is grounded and here it's output. Here it is your input. Now the options are, first the question is, the circuit shown in the figure uses ideal OPAMP amplifier. For small positive values to V in, the circuit works as. This circuit, given circuit works as, option A is half wave rectifier. Half wave rectifier. Option B is differentiator. Differentiator. Option C is a logarithmic amplifier. Logarithmic amplifier. And option D is exponential amplifier. Exponential amplifier. Okay, friend. Friend, this is not differentiator because we have seen the differentiator circuit. In the differentiator circuit, at this stage I have capacitor and this stage I have feedback resistor. Let me check over here whether it's a half wave rectifier is given or not. So half wave rectifier come to the positive half cycle. In the positive half cycle, it will be negative. Negative means a direct diode will conduct. You will get some output. Definitely will get output. Okay. What about the negative half cycle? And the negative half cycle, you will get positive over here. Is it okay, friends? And so in that case, when this is negative, positive will be over here and your diode will be negative bias, reverse bias. It will be open. If it will open, then also we'll get the output. Why? Because this open circuit now. In the open loop configuration also, we get the output. Okay. So in both cases, we are getting output. So this is not half wave rectifier. This is not differentiator. So this is the circuit for logarithmic amplifier. Okay, friends. This circuit is given for the logarithmic amplifier. You can remember it like this. The logarithmic amplifier circuit is given in this way, but still we can derive this. Okay. The diode is given over here. If you remember, in the diode circuit, we have seen the current across diode or in the diode is ID equal to Is e to the power Vd divided by eta Vt. This was the current given for ID. So given into the diode. So into this diode circuit, though this is the 0. So current over here is V in by R. So V in by R is the current over here. This is the, and this is I naught. Let's take it I naught. Saturation current. So ID is given, or ID, this is the current into the diode circuit ID. ID is I naught e to the power. The voltage across this, let's take it Vd divided by eta Vt. Eta will take 1 over here for the silicon circuits. Okay, friends. So what is ID over here? This Vn by R current will come into this, and this is nothing but the ID itself. So V in by R is the ID. This one will be equal to I naught e to the power. What is Vd? Vd is the voltage across diode. And this, if you will follow this circuit or this loop mesh, you will get the voltage relation between Vd and V naught. Let me start from 0. From 0 I'm getting minus Vd. Okay, minus Vd. I'm terminating at V naught. It will be minus V naught equal to 0. So V naught equal to minus Vd. So Vd equal to minus V naught. So I can, instead of using Vd, I can use minus V naught over here. And this is Vt. Okay, friends. So I need the output. What output I'm getting into this circuit? So everything will go to that side. So it will be V in divided by I naught R equal to E minus V naught Vt. Let me take log both sides. So it will be V0 and this. So finally I'm getting, let me erase this. Finally for this circuit, what I'm getting is, you are taking logarithm of input. Okay, see over here, the equation we are getting is ln V in by R. I naught is also given over here, is nothing but minus V naught by Vt. This Vt will come to this side, this minus will come to this side, and this side we will remain it with V naught only. So your output is nothing but, you can see over here, logarithm of input. So this is logarithmic amplifier. Is it okay, friends? So let me take next question. The circuit of the question is 100K, Vi is minus 1 volt. This is Vi, okay? The circuit minus plus like this. Here the diode is given 4K and V0. This is given over here. Now the question is, consider the following circuit using an ideal OPAMP. The IV characteristics of the diode is described by the relation. The diode current is given I equal to I naught e to the power V by Vt minus 1. This is given, where Vt is 25 millivolt, I naught is 1 micro given. I naught is 1 microampere given. Vt is 25 millivolt. We know this. Okay. And V is the voltage across the diode. I'm sorry. So this is the voltage V and this is the voltage across diode. Okay, fine. Now the question is, for an input of Vi equal to minus 1 volt, what is the output they are asking? What is the output voltage V0? For V in minus 1 volt, what is the output they are asking? This is the question. And you have options A equal to 0, B 0.1, C 0.7 and D 1.1. Okay, friends. So this is the diode given over here. In this circuit, the current is, this is 0, this is minus 1. Definitely current direction will be like this, and it will be 1 by 100K, 1 by 100K. The current direction is from 0 to this side, means current is originally coming from this circuit. Okay, because the OPAMP does not take any current. So I know the diode current now. Diode current is 1 by 100K, means 1 by 10 to the power 5 is my diode current. This is equal to I naught. I naught is 1 micro. E to the power V by 25 milli minus 1. Okay. So from this equation I can find out V0, the voltage across diode. If I can find voltage across diode, later I can find V0. So let me find this first. So this is 10 to the power minus 5. This is 10 to the power minus 6. So I'll remain with 10 to the power minus 1 and it will go to this side. It will become 10. E to the power V by 25 milli minus 1. Now you can solve it by taking log both sides. And then at the end you will get V equal 0.06 volt. Now you calculated the voltage across here. Now you need what is the voltage V0 at the output. Okay, so let me do that one. Is it okay, friends? Directly they have given the diode current. You have to identify the diode current in which direction it will flow in the circuit. Then you have to answer. So now let me show you. They're asking for the V0. How to find V0? This is the V0 over here. In this circuit I know the current also. The current is 10 to the power minus 5. Perfectly fine. The current is potential difference divided by resistance. Here is the potential V0. Here is the potential with respect to ground is given. It's V 0.06. You just find it and divide by 4K. Divide by 4K. So when you will solve it, you will get for this circuit V0 0.1 volt. So in which option is given? Option B is correct. Okay friends, this was the 2 marks question. Let me take another one. So the circuit for this question is given VIE connected with 2K. Over here I have diode. This is again logarithmic amplifier V0 minus plus. This is grounded. Everything is like this. Now circuit question is, in the OPAMP application or amplifier circuit shown, assume that the diode current follows the equation I equal to, the diode current is given over here also, I equal to IS e to the power V by Vt. V by Vt. So V is the voltage across diode. Remember always, okay? Now the question is, if Vi equal to 2, they are saying if Vi equal to 2, they are getting output V01. If Vi equal to 4, they are getting output V02. Now the question is, what is the relation between V01 and V02? The relation between V0 and V02. So V02 is given √2 of V01. Option B is given V02 is E square of V01. Option C is given V02 is V01 of ln2. Option D will be V01 minus V02 equal to Vt ln2. Okay friends, this is given over here. Now let's find one by one, find out V01 and then V02. V01 is the voltage at the output stage when input is 2 volt. So when input is 2 volt, the current in the circuit is 2 by 2K, means 1 by 1K means 1 milli. So 1 milli current you have to compare with this. This is Is e to the power. You have given this V now in this case. No, they have given only Vi2 and V0 given. In this case it is V01. Output is V01 and output will be related with minus with this. So I can write is V01 divided by Vt. This is equation 1. The equation 2 is when Vi equal to 4. So in this case it will be 2 milli. 2 milli, everything is same. E to the power, this will become V02 divided by Vt, equation number 2. Now you have to find out the relation between V01 and V02. Let's divide these two equations. Milli milli cancel. This will be 0.5. Let me take over there. I need some space. Okay. So finally equation you are getting is 0.5. This is the 0.5. Is will cancel out. E to the power, this is the E minus V01 by Vt, and this will become E to the power minus V02 by Vt. Okay friends. So denominator term I can take up. So these two terms will be added. V02 by Vt, and this will be cancelled out. This will go away. Raised over here. Okay. Now both sides I can take ln. So it will be ln 0.5. this side you will remain with V02 divided by Vt minus V01 divided by Vt. Okay friends, Vt is common in both the sides. So your option is this. You can easily take it. Oh, I have to arrange in this form. Let me show you. Wait a minute. You are getting answer but not given in the option same whatever you are getting. So you have to manage it and arrange some values so we'll get the correct thing. 0.5 we are getting. Vt will multiply over here. This side you will remain with V02 minus V01. This is we are getting. But nowhere it's given. Here it's given but V0 minus 1 and V02 here ln2 is given. Okay friends. So we are having ln 1 by 2. So when it will be inverse it will be minus. So V2 ln2 with minus sign. And so it will become V0 1 minus V02 with minus sign. It will be like this. This is your option D over here. Okay friends. So let me take another problem over here. Now I'll take question in which BJT and OPAMP are combined. This is 2013. Very funny question and 10-second question. Only 10-second question. You are conceptually strong, you can click it. This is 1 mark question actually. And the question given is, circuit is given over here. Minus plus, I'm sorry, this is grounded. Here is V output. And this is connected with 1K. This is connected with 5 volt. Here we have BJT circuit like this, and this base is grounded. This is Q given over here. Now the question is, in the circuit shown below, what is the output voltage V naught? If a silicon transistor Q and an ideal op-amp are used, your options are given. Option A is minus 15 volt. Option B is given minus 0.7 volt. Option C is given 0.7 volt. Option D is given 15 volt. This is the question, 1 mark question and hardly 5-second question. But some students will solve this circuit like they will start, it will be 0, they'll find out current will go this side, no resistance is there, what I have to do. This is the question in which you have to follow the KVL mesh analysis. You have to start from somewhere, you have to reach to somewhere. In this case, this is the drop over here. I have to start with this ground. Let me start 0. Here I'm getting minus 7. Here I'm getting minus 7. At this terminal I'm getting V0. So this is minus V0 equal to 0. V0 equal to minus 0.7. So this is in 3 seconds you are getting the answer. So that's why I called it funny question. So sometimes they ask the question like this. Okay. Let me take another problem. So let me finish this chapter with differential circuit question. And the circuit is like connected like this. This over here, it is VI. Over here, this is I0 in parallel with RE. Always the resistance with current will be parallel. This is minus VEE. Over here I'm getting RC. Okay, let's take it. RC. And here VCC. Here I'm taking V0. V0 over here. Okay. Now the question is, this is the terminal where we apply the V in like this. Plus minus. Here V in we applied. Now the question is, in the differential amplifier shown in the figure, the magnitude of the common mode and differential mode gains are common mode ACM and differential mode is AD respectively. If the resistance RE is increased, this RE is going to increase in this case. RE is going to increase. Then if this is increased, then, and you have 4 options. Option A, ACM increases. ACM increases. B, common mode rejection ratio increases. CMRR increases. AD increases. Option C, AD increases. Or common mode rejection ratio decreases. CMRR decreases. So in the last class only we have seen the CMRR is AD divided by AC. AD we calculated there. AD equal to GMRC minus GMRC, and AC also we have seen the AC was RC by RE. Okay, AC was dependent on this RE. So here what we are going to do is, we are increasing the RE. When RE will increase, AC will decrease. So AC is going to decrease. Do we have any option here? AC is going to increase option is there. Now AC is decreasing. What about CMRR? Definitely by this formula, CMRR is nothing but AD by AC. AC is going to decrease, CMRR going to increase. So correct answer is CMRR going to increase. Okay friends. So friends, this is all about the third unit, operational amplifier, in which in this unit also I joined the feedback amplifier. So in the last unit we have remained with oscillators and power amplifiers. We'll come soon and we'll meet soon over there. So friends, let me tell you one thing. Please do practice at your home. Okay. So we'll meet in the next. Till then,